not to, but yeah, okay, so just to repeat, so the final exam will be posted no later than 8 p.m. Tuesday, the 14th of December. That's a week from today, I believe. And I believe that's the day after the last day of official classes. Like, we don't have class that day, but you would have had classes all the day before. So it's basically the beginning of final exam period. The final exam will be posted that night, no later than 8 p.m. that night. It will be due back no later than Sunday night, December 19th. It's take home, it's open universe. The details of it will be updated as we get closer in Google Classroom, but the main details of it right now are in the posting in Google Classroom that says practice prep for final exam. And again, just to repeat for anybody who just joined later, just to be as clear as I can, your final exam will be a few problems taken pretty much directly from the two documents posted there. Those are an old midterm and an old final exam. Your final exam will be problems taken from those documents, and you will have a choice as to how many problems you actually, I mean, not as to how many, but you will be asked to do like 2 long problems and 7 multiple choice problems or something like that. And you will choose what you're comfortable doing, and you'll do it, and you'll do the best job you can. You'll show as much work as possible. Oh, and this was the thing I was about to say before. And again, it's open universe, meaning not only do I allow, but I encourage you. Now that you'll be able to see the document from here on in. There won't be any surprises of what it is that I'm asking you to submit. So you can and should talk with one another and work through these problems. Like some people about going back to September or whatever, but work with one another to get solutions to the problems in those documents. Whatever you find in the final exam will come from those 2 documents. It won't come from anywhere else. So work with each other, help each other, figure out the solutions to those. And that's not cheating. The one thing is that when you sit down to actually write out your final exam and submit it to me by Sunday night, the 19th, you just make sure that everything you write down, you understand by the time you're writing it down. And the more you understand, the more you'll be able to write down. The more you get your answers, the more work you should show. Remember that I already know the answers, and I know that you know the answers or can get the answers. So you're trying to show me in your final document, what you're trying to do is really prove why the answers actually make sense and prove that you actually understand the sense of those answers. So the more you can say, and the more you can say it your way, and the more colors you can use, or the more diagrams you can present, the more you will dazzle me with your comprehension of the material that you choose to show me that you understand. And it will be your choice. The last way I want to put this whole thing, but I really do mean it because I know it's stressful times. I get stressed by all this. I really want you to, not only are we in a team together trying to get you to know physics, like my dream is that you like and understand physics, but also we're here to judge you. I hate the word judgment. We're here to assess you and give you a grade based on your best, not based on your middle, not based on your worst, not based on your average. Based on your best. That's my philosophy. So you're going to choose the parts of this course that you really understood, and you're going to show me that you really understand those parts. I'm not here to find out that you never missed a moment. I'm not here to find out that you get every piece perfectly. I think that would be a dishonest standard. I don't think I get every piece perfectly. I'm here to have you show me what you think is the part that you took away the most and the best, and show me your best version of that. So it's designed so that you have an opportunity to show me why I should give you an A. And I'm here to listen and be like, yeah, she's right. Or he's right. I totally want to give that person an A. And in fact, I'm not giving it, I'm just computing it. And there it is. Okay. So hopefully that sort of makes sense. Now, I want to like try to wrap up the material to some extent possible. We've got like 45 minutes. I'm saying all this. I know we have one more class after this. but there's a little fear and panic in my mind that something is, I have some reason to believe on my end that something may go wrong that day, and you may get an update from me. I don't want to miss the last class, but it is possible. So I'm also acting. So if we do have that opportunity, definitely what you really should do is look at this practice document between now and then and come that day prepared with questions about the practice document. But if, quark forbid, we don't see each other again on Thursday, I will stay in communication with you all, and I will post updates and further details and stuff about the final. But let me one last time remind you, hold on, just in the chat. Okay, so just in case, as we, if there's any questions about material or about the final or stuff like that, please feel free to text me to say who you are. And that's my number in the chat. So, I mean, I'm hoping to see you again Thursday, which I believe is our last class, but I'm actually suspecting there may be a problem that I can't solve. And I'm just sort of warning you of that, in which case, of course, I'll alert you if that happens. All right. So is it basic? Let me just ask quickly. So we have like 45 minutes to do some, to wrap up some material here. Is it more or less clear what I'm saying about the final exam and everything? I mean, can I just get some kind of yes or something in the chat? Are you with me about the, yeah, okay, great. Thank you so much. And that's all points. That's all points. Thank you. Oh, and you, oh, very clear. Oh, thank you. Great, great, great. Okay. Oh, and you just, because your enthusiasm, and I appreciate your responses. You also just reminded me, I still have some, loose ends to turn back to some of you, and I'm aware of that, and they will come back. And I will hopefully, I think I promise this, hopefully you'll have real grading, like clear grading information before you take this final, hopefully, I think. But also it goes both ways. Classes don't officially end till next Monday, even though, so yeah. That's exactly what I was just, thank you, direct chat person. That's exactly what I was just about to address. Any loose ends that you guys have for me, any old assignments that you still want to turn in for points, or game assignments, particularly any of those special game assignments that are not just game turns, but are game, any of that can be turned in at any time through Monday of next week, because Monday is the last day of classes. I will accept any and all of those things through Monday of next week. I'll try to even change the due dates on some of them so it's not confusing. But yes, you can still turn in all that stuff by Monday. Now, I would suggest in many of your cases, if you've turned in a bunch of that stuff and got a bunch of that stuff back, in many of your cases, it's probably better to just focus your attention at this point on the final. But yes, I will take anything and everything for people through Monday of next week. Great. Yeah, hopefully that answered that question. But yeah, I was just about to say that. Yeah. Okay, wait, what was that? Great, thank you. Thank you. I appreciate it. Okay, so let me try to tie together some things. Like in the lecture, I've been talking about these sort of abstract things known as electrostatic fields. And then the last class, we got into field lines, which seem even sort of more abstract in a way. But if nothing else, fields, we believe, exist everywhere in space, right? We believe that every object, every charge, every mass creates a field which extends everywhere in space, and which we think of, we picture as these lines going through space. We don't really literally believe that there are literal mechanical lines in space, but we picture these lines, and what the lines represent is the existence of true, actual information that is everywhere in space due to every single object that's in space, right? Like the ultimate thing I want you to recognize and take away from this abstract discussion of fields is that we believe that when things exist, the information of their existence, like how big they are and where they are, is somehow sitting everywhere in the universe in what we call a field. It's like a field of information. And we picture that information with using these lines in our mind. But the actual reality that we think is that there's information in space everywhere due to every object. There's information due to every charge, there's information due to every mass, right? And that's what we've been talking about in lecture. Then in lab, you've been dealing with these electronic or electric circuits. I mean, of course, simulations because we're, on the internet and everything, but you've been talking about circuits. an electrical current. Not entirely clear necessarily what the connection is. Clearly what you're doing in lab has to do with electricity. And what I've been talking about in lecture has to do with electricity, but it may be very unclear to you what the connection between the two things is. It certainly was unclear to me for a long time. So let me start by telling you this. Okay. Here's what current is. Well, first of all, I almost remember. Okay. Okay. Remember, every time we were talking about field in class, Q stands for charge, right? And remember, like the charge measured in coulombs. So like the charge of a proton is 1.60 times 10 to the negative 19th coulombs. The charge of an electron is negative 1.60 times 10 to the negative 19th coulombs. So coulomb is actually a huge amount of charge. It's equivalent to like about 16 quintillion protons being smashed together into a tiny, tiny volume. But that's what we mean by charge, and that's what we mean by Q. What electrical current ultimately is an amount of charge in a line, dq over dx. So like an infinitesimal amount of charge per an infinitesimal amount of length. Like dx means like delta x, but taken to the limit where delta x approaches 0. So dq dx is a one-dimensional density of charge, a infinitesimal line of charge, you could say. dq over dx is a thin line of charge, a certain amount of charge per certain amount of length. Imagine that little line of charge having some velocity, dx dt, right? Dx dt is velocity, you remember from physics 1, infinitesimal rate of change of position per time. So if we take a little line of charge and we give it some velocity, thereby we let it move, we multiply the two numbers together, we're saying that the bigger either number is, the bigger the whole amount is. Now, if we when we define current, or we put together the idea of current in our minds, what we're putting together in our mind is a line of charge with some velocity. When you multiply the two together like that, you notice, even though you can't always do this with infinitesimals, you can sometimes, you notice that in effect the dx's cancel, or it certainly looks like they cancel. And what we're left with is dq over dt. That is the true definition of charge. What does it mean? Why am I making a big, excuse me, it's the true definition of current. Now, why am I making a big sort of deal of this? Why am I writing current this way? I'm trying to emphasize to you that when you're picturing a current, you should picture a line of charge with motion. That is what a current is. It's a moving line of charge. But when you really think that through and think of what it means to attribute some velocity to a line of charge, if you think of the dx as canceling like that, or when you think of the units that you're doing, if you think of units of coulomb per meter times meter per second, and you realize that the meters are going to cancel out, what you're left with is this ratio, this infinitesimal ratio, or this rate of change of simply coulombs per second. What does that mean? It means that current, I mean, that's the true definition of current, okay? Current is the derivative of charge with respect to time. Like if you're comfortable with calculus, then there it is for you right there, that what current is the time derivative of charge. But what are we saying when we're saying that? We're trying to emphasize that current itself is a body of moving charges, yes. But when we measure current, we're not measuring how fast some given electron moves through a wire. Like when we talk about current, we're talking about electrons moving through a wire. And when you do all these labs with current, voltage, and resistance, you're supposed to be picturing a bunch of electrons moving through these wires. But when we take an ammeter and put it to the wire and measure, oh, the current in this wire right now is 400 milliamperes. What we are not saying, oh, each one of these electrons is moving at a rate of like 400 miles per hour or something. That's not what we're saying. When we measure current, we're not measuring how fast any individual charge is moving. What we're measuring is how many charges are flowing or passing by a given point in space per a certain amount of time. Like please notice, like, and I know many of you probably already knew this in a way, but I'm just trying to, say it in a certain way. Current is amount of coulombs flowing or passing per every second. So when we say there's 400 milliamperes of current at a given spot in the wire, what we are saying is we imagine ourselves standing at that spot in the wire at a particular location. Notice whenever you put an ammeter, or whenever you make a current measurement of a circuit, even if it's a simulation on the computer, you place the ammeter at a certain location in the wire. And at different locations, you might get different results. But you place it at a distinct location in the wire, and you get a reading like 400 milliamperes. What you're saying then is, aha, if it's 400 milliamperes, you're really saying, oh, 400 millicoulombs of charge are flowing past this location every second. Like you're saying a certain number of electrons are passing this location every second. To measure current is equivalent to standing on a highway and counting the number of cars that pass by you per moment. It's not equivalent to putting a speedometer or a radar gun in any one of the cars and asking how fast it's going. It's counting cars, not counting the speed of cars. Follow? So that's what current is. Now, why am I making a big, so stop me if that doesn't make sense so far. But so to measure current, all of this is to say that what current is flow. When we say the current is high in a given wire, we mean there's a lot of flow passing by a given location per a given amount of time. Flow of charge. Now, charge is a real thing. Electrons are a real thing. But whenever we But yeah, charges are a real thing. Charges are actually moving in the wire in order for this flow to occur. However, okay. So I'm saying when we picture current going through wires and out of batteries through resistors and into light bulbs and so forth, we're picturing electrons running around these wires. And again, by the way, we're always picturing electrons because electrons can become free, right? Electrons can become ionized. Electrons first exist in orbitals of atoms, and they can pop out of those orbitals and actually run around on their own, unlike protons, which are trapped in the nuclei of atoms. So we're generally always thinking about electrons as charge carriers, and that's why we call it electricity, not proticity or whatever. So electrons are real things. These little containers of charge, these little packages of charge are real, material, discrete, particular items. And they supposedly are the things that are running around these wires and creating electric field and doing all this other abstract, cool stuff. But again, remember, when we measure current, we're not measuring how fast any one of these objects is going. It's not really physics 1 anymore. We're not actually doing the kinematics of a given electron when we study electron. We're studying the flow or measuring the flow of electrons in general through the wire. So it raises a question for a minute, especially since this is like the end of the semester, like, okay, electrons are real, material, particular, thingy things. Is flow, I'm asking rhetorically, is flow, current, a real, particular material thing? I mean, if it's not the speed of a thing, if it's a count of a number of things, is it a material thing? And the answer is no. One of the reasons electrical current is a cool thing to study, an important thing to study, and a cool sort of way to end the semester is I want to point out that if I'm standing here in a wire, and I'm counting how much charge flows past me in a given second, like how many coulombs of net electrical charge pass me in a given second, I don't have to actually identify specific particular electrons going around. The electrons don't have to behave like race cars. there doesn't have to be any one single electron that actually goes around the whole track and completes the circuit and then comes back in front of my face again to be counted again next time. I mean, even though we talk about circuits, as being closed loops, and they most certainly are. And even though no circuit will work unless the charge keeps flowing around and around and around, the fact of the matter is, there's no reason for me to believe in or expect any given electron to be going all the way around the track and coming back in front of me every single time the current seems to make a lap. In fact, there's no particular reason for me to insist on or believe in or expect any given electron to be going very far at all in the wires. When we say we're studying electrical flow or electrical current, we are studying a motion that could not exist but for these electrons. But just like sound, there's no reason really actually to expect or believe or insist that any given electron is doing the whole motion that we say the current is doing. What I'm really trying to say is, one of the reasons we spent so long on sound, we spent so long on harmonic oscillation, from which we built wave propagation, from which we built sound and the intricacies of sound and the Doppler effect and all that, is that sound really is a fabulous way to understand so much of what's happening in the universe. It's not the only way to understand, and it's not even necessarily ultimately the best way, but it's a fabulous way to understand a lot of phenomena and a lot of motions that occur in the universe. One of these motions is electrical current. The fact is that electrical current, yes, it consists of electrons, it consists of charges. And yes, since 6th grade, perhaps for many of you, we've always been discussing the flow of electricity through wires as though you're supposed to be picturing little electrons going around the whole wire from the positive pole of the battery to the negative pole of the battery. But now that you've spent all of this time looking at, in this course, looking at propagation and looking at unthingy motions, I'm here to tell you that that's a much better way to understand the magic of electricity. No way of understanding anything is perfect. Like, just like the best way to understand fields is by picturing field lines, but that doesn't mean I'm asking you to believe that there are actual literal lines in the universe. Anything we ever picture and do in our head, including math, is some kind of metaphor or analogy for what's actually going on. We will never be able to perfectly access what is actually going on. We are just trying to come up with the best approximations and models that we can to enable us to make accurate predictions, right? That is our job as scientists. We do not think we have access to the absolute truth. We think we have access to data, and from data we build models, and from models we predict further data, right? So to that end, if you understand that that's how to understand science in general, then I'm here to tell you that if you're going to be picturing electrons going around wires from one pole of a battery to another pole, as long as you're picturing that at all, don't picture a series of electrons running around the whole wire. Picture a little electron here that goes back and forth and back and forth. and another electron next to it that goes back and forth and back and forth, and another electron next to it that goes back and forth and back and forth. And each little electron does some sort of Brownian, right? You've heard of this, like random drifty little motion within its little neighborhood. These electrons don't really travel very far. I mean, angstroms are huge distances to these electrons. They're just vibrating around and oscillating around and banging around in these little neighborhoods. So one little electron bangs around here and it causes vibration to the next electron. I mean, electron repulsion causes vibration in the next electron over here. And then the next electron vibrates over here. And what flows through the whole wire is actually a pulse of charge, much like a sound pulse propagates through oscillating air molecules. Okay, and I'm not saying the analogy is perfect, and I'm not saying that it all translates perfectly, but it translates a lot better than any other analogy we have. I'm saying, and I'm using the word compression wave here to remind you also, remember the original kind of waves that we ever studied on strings were transverse, like the string is a horizontal medium like this, and you pluck a little bit of the string and it vibrates up and down vertically, right? And so you have oscillations along the y-axis causing propagations along the x-axis. The two motions, the oscillation of the individual particles and the propagation of the whole pulse are perpendicular to each other, are across from each other. So we call that transverse. That would be like, like a pulse on a plucked string, or like a water wave on the surface of the ocean would be transverse. But then we started getting into sound waves where we said the air molecules, they don't actually vibrate up and down while the sound propagates horizontally. It's the air molecules themselves sort of oscillate back and forth, and they compress and they expand, and compress and they expand again. So we call that a compression or longitudinal wave. I'm saying what electrons do in a wire is a lot closer to that than to anything else we've ever discussed or that you can picture. An electrical current is really a compression propagation of charge. So this is another example. So electrical current, which is so powerful and so real, right? Like obviously it's everywhere part of our lives. In and of itself is another example of motion through space that is actually immaterial, non-particular, non-massive, non-thingy. When electrical current flows, not only is something as microscopic and somewhat difficult to grasp as charge flowing, but I'm here to tell you that, in fact, the charge itself is not flowing. A pulse of charge is flowing. That's what electricity really is, or is closer to what electricity really is, okay? And that's part of why it's part of this course and it's worth studying. And so you can understand it with so any of the math that's involved in the midterm document that has now become your final exam is just as applicable to electrical charges as it is to sound pulses. Okay, that's one thing. We still have 17 minutes. That's one thing. Now, again, I'm rushing a little bit here. I'm going much more big picture now than usual, or I'm maybe less mathematical than usual because I'm just trying to tie together loose ends of this course and show you where we've been and where we're ending up. But again, just always bear in the back of your mind that the emphasis of this course is immaterial motions, non-thingy realities, right? The first example ultimately was a wave pulse, something that's very real, that moves in a measurable, predictable, analyzable fashion, but is not material, discrete, massive, particular, or identifiable, right? That was our first example, was a wave pulse. Then we got into electric fields and gravitational fields, which are, again, example of something in space that is not material, something that is not matter, but nonetheless seems in every scientific way to matter, right? That's what a field is. Field is information sitting in raw, empty space and affecting the motions of physical bodies through empty space. That's what a field was, right? And masses, just by existing, created gravitational fields, and electrical charges, just by existing, created electrostatic fields. Now, I'm here to tell you that when electrical charges move in a certain wave propagatory kind of fashion, when charges start undergoing harmonic oscillation, when a bunch of charges get together and start oscillating in a phase staggered pattern kind of way, they create this ripple through the charges called an electrical current. And that's what you've been studying in lab. Now it goes one. So that's like a pattern of patterns in a way. It's like immaterial in a way. But now I'm here to go one step further on one of our last days of classes, if not our last, and say that actually, it turns out once you have a bunch of charges that are collected in a line, all those charges just by existing will create electric field. Like they will plop the information of their existence everywhere in space and affect the motion of everything else that exists in space. But if you put them in a line and if you start them oscillating in a collected phase staggered pattern way, in other words, if you let a pulse run through these electrical charges, we will observe that pulse to propagate through and call it an electrical current. We will measure that current in ammeters. And it turns out that the existence of that current, that steady current now there's like steadily electricity going through this line of charges, in our ammeter, it says 400 milliamperes or whatever. That steady current that now exists in the world, it creates a field. It sends its information out into the world of where it is and how large it is. And that information that it sends out into the world is called a magnetic field. And I mean that literally and mathematically. Again, I'm going a little bit fast there. I'm going a little bit abstract today. But in the same way that just by existing as a mass, you automatically create a gravitational field, you convey your property, your numerical identity, your vector influence, you convey it through the whole universe in a manner that we call a gravitational field. In the same way that a mass creates a gravitational field and a charge creates an electrostatic field, a current, it turns out, creates a field that is different from the other two, very related, very similar mathematically and all that, but yet its own field, and we call that thing a magnetic field. Literally, a magnetic field is all the information contained of a steady current. Why do we believe in such things? How do we believe in such things? I'll tell you quickly. You can write this down or not as you see fit. Because it turns out in the late 18th century, early 19th century, people were getting very excited about electricity and electrical currents. Americans like Ben Franklin for real were, and Europeans, people were playing Volta, the voltaic cell, all that kind of stuff. People were doing a great amount of controlled experimentation with laboratory electrical currents. And a number of people in a number of countries simultaneously realized, including this guy Ampere and this guy Oersted, realized that if you put, in fact, let me write this. it turns out that if you take two wires, place them near each other, isolate them from other effects, if you just have two wires and you put them near each other, nothing happens. They just sit there. Like there might be a bunch, there's probably a bunch, there definitely is a bunch of protons and electrons in one wire, and there's a bunch of protons and electrons in the other wire, but presumably there's an equal number of each in each. So whatever the protons do to repel the protons in the first wire will be balanced by whatever the protons in the second wire are doing to attract the electrons in the first wire, et cetera, et cetera. So you take these two wires, they have a bunch of charges in them, but they won't electrostatically attract or repel each other at all because of equal number of charges. But then you turn a current on in each wire. Say you turn the same amount of current on in each wire, and say you run the current through both wires in the same direction. And that's what I really mean by parallel. Parallel means same direction. If you run current through these wires in the same direction and same everything, it turns out these wires will come together. Now you might say, oh, well, that's not that surprising. I mean, you ran current through the wire, so like you put extra charges in, and we know that there's electrical forces and electrical fields between charges. So that's not really, is that really that big of a surprise? Well, it's just enough of not a surprise that people set up this experiment and thought something was going to happen. It's just reasonable enough that this experiment was done by Ørsted and Ampere and other people over and over again at the same time. And it was just unsurprising enough that they did bother to set up really controlled conditions for this apparatus. But what's surprising is the details. Think it through for a minute. I'm saying that if you put no current in these wires at all, they just sit there. But if you run the same current through both wires in the same direction, the wires come together. Now, and in fact, to go a step further, if you're following what I'm saying, it's weird that they come together. In other words, like you might think, oh, electricity. Yeah, I know about electricity, like proton. But if you're running the same, first of all, there were charges already in the wires and nothing was happening. Now we're just running charges in motion through. We're just sending flow through. We're not necessarily giving either wire extra charge. We're just saying, let's send a flow through each wire. That should not necessarily change the number of charges. It just means that there's a flow now. Now, even if you say, yeah, but that seems funky. I mean, as long as some charges are flowing, that means they're going to be sort of counted differently from the charges that are sitting around or something. That's all fine. Maybe that is true, except we're sending the same flow through both the wires and the wires attract. This is the surprise. Enough people thought something might happen if we turn electricity through two wires that they set up the experiment. But what's weird is that the wires didn't repel as you would expect from everything we know about electrostatics. Like we assume protons repel other protons and electrons repel other electrons. And it takes two opposite things to make an attraction. But if you send the same current through both wires, the wires attract. And so much so, it's so much not a fluke or some weird thing that if you actually turn the current around in one of the wires, this is a test that was done, so that you send opposite currents through, then the wires do repel. Or not the wires, the currents do repel, and they come apart from each other. In other words, oh, and I should also add, the more flow you send through, like the higher the current that you send through in either of the wires, the greater extent to which this phenomenon occurs, like the faster the acceleration. So this is another example of action at a distance. This is another example of something happening through empty space. This is another example of somehow the information of something going on over here is somehow affecting the thing going on over here through empty space and creating some kind of force of repulsion or attraction. But the force is happening through empty space. So they said, and we said today, oh my God, that's another field. And we already know about electrostatic fields. It's not electrostatic because it's happening in a weird direction. It's not gravitation because it would be happening all the time, because gravitation would be happening anyway, whether or not the things are moving, and it's not. So it's a third kind of field. It's a third kind of action at a distance. And for centuries and centuries and centuries, there's been one kind of action at a distance that everybody's experienced in the world and everybody's built compasses out of and everybody's navigated, as a result of, and everybody's built fun. And that is that everybody's known for centuries and centuries that iron somehow affects and pulls on other pieces of iron through empty space. Everybody's called this thing magnetism forever. But no one's ever had a mathematical or physical formulation of why or how this thing works. We've just known that iron seems to pull on and push on other iron in the same way that the earth seems to pull down on macroscopic objects. So, and iron is metal. So the guess was made, the conjecture was made that turned out to be right and established that ultimately that phenomenon that we never had a physics understanding of, but the world had a deep working familiarity with, that understanding must be linked. That action at a distance that's never been explained before must be linked to this action at a distance that's now happening on a microscopic level, that's happening in some way that's related to things that we're now beginning to understand, which is charges and flow and the flow of charges. So it was posited, and correctly, but we still believe this to this day, that in the same way that a sitting charge creates an electrical field, a moving charge, a flow of charge, a current creates what we're from now on going to call a magnetic field. Okay. And then it turns out that what is iron? Iron is a material made of a bunch of atoms, just like any material is made of a bunch of atoms. But most materials are made of atoms that are all in random alignment. Every single atom has like a little, at least one, like every single hydrogen atom has an electron going around and around, a little natural current loop that's creating a little bit of magnetic field. But in most materials, all the atoms are all like randomly aligned. So you've got a current going this way and a current going this way and a current going, and they're all canceling each other out in most regular materials. But it turns out that certain materials, like certain metals, like iron or magnesium and stuff, have all of their electron orbitals somehow more or less nicely lined up, or iron is the name we give to materials that happen to have all their orbitals nicely lined up. So you have a bunch of natural occurring currents in a metal like iron, and all those currents set up magnetic fields that all line up and reinforce one another, so that at the end of the day, certain metals like iron actually consist of a bunch of little internal currents that are all making magnetic fields. I have 3 minutes left. Why am I saying all this? I'm trying to say this, just to wrap up everything and just to give you an English perspective on all this material. Sitting charges create electrical field. Moving charges create magnetic field. It also turns out the beginning of the Industrial Revolution began with something called a Faraday's discovery that you probably learned about in middle school one way or another. It turns out that if you move a magnet in a certain way, if you change a magnetic field, you'll create an electrical current. Flow of electricity creates magnetism. The motion of magnets, it turns out, creates electricity. If you set things up in a certain way, and I know I have 2 minutes, but if you set things up in a certain way, if you create an electrical current that is not steady in time, if you create an electrical current that is changing in time in some sort of, say, co-sinusoidal way, if you have a current that, and give me like 1 minute if we go over, I mean, if you have to go, but I'm going to go like 1 minute over, but then we're done, and we might be totally done, we might not, but just hear me out for 2 minutes. I think this is worth it. But if you have to leave, leave. But listen, just to bring this all full circle, imagine setting up a current that changes in time as a cosine function of time, like a current that's like I naught, like some value, times cosine of omega times t. A current that gets bigger and smaller as time goes on, bigger and smaller in a cosine way. That current will make a magnetic field. Magnetic field will get bigger and smaller in a cosine way. The changing magnetic field will make an electric field that gets bigger and smaller in a cosine way. The derivative of cosine is negative sine. The derivative of negative sine is negative cosine. The derivative of negative cosine is sine. The derivative of sine is cosine. No matter how many derivatives you ever take of a cosinusoidal current, you'll always get another function, right? There's nothing about the cosine function is ever constant. We saw that at the beginning of this course. If you create a current that is cosinusoidal in nature, that has an infinite number of derivatives, automatically, you'll create an infinite number of changes. You'll create a current that creates a magnetic field, a magnetic field that's changing, so it creates an electric field, an electric field that's changing, so it creates a magnetic field, a magnetic field that's changing, so it creates an electric field, and on and on and on. And these oscillations, these fields that keep changing, will literally fly out from the current into space. Like they will change all that information that is already everywhere in space that we call a field. If we say the field is changing, it means the numbers everywhere in space change. If we say the numbers change again, it means the numbers change again. These ever-changing amounts in the field that are created by a cosinusoidal current will ripple out through space, ripple through those lines of field that are everywhere in space, and cause perpetual pattern of patterned changes in the information everywhere in space. These changes will ripple out as a wave propagating through the medium known as electric and magnetic fields. In other words, if you create a situation where the electric fields are changing the magnetic fields and the magnetic fields are changing the electric fields, and on and on and on, what you create is a propagating pulse through the electric and magnetic fields that already exist in space. That pulse will go out according to the wave equation. It will go out at a certain speed as dictated by the wave equation. The field, look at the very last statement on here, will go out and satisfy time derivatives and space derivatives just as any wave will. And the speed at which that pulse will propagate turns out to be the speed of light. What light is an ever-changing, patterned, propagating, pulsing change in the electric and magnetic fields of space. Light is the sending of information from one point in space to another. Light is ripples in the electromagnetic fields that exist everywhere in space. Anytime one object changes its mass or its charge or its location, the new information of that ripples, propagates, pulses through the fields to all other objects, and does so at the speed of light. Light is the transmission of physical information through the fields of space. That's the point of all of this. I know that's a lot. I'm just asking you to just take it however you want to take it, as maybe hopefully a reason to take more physics or a reason just to appreciate light. So that hopefully I'll see you Thursday, but if I don't, that's it for today. Thank you for hanging in. And you've been a great class, and the more updates on the final will be updated. Okay.